Hi viewers, welcome back once again to end of our classes. So in today's lecture, we'll solve some more numericals from the chapter Electrostatics, and that is the problems regarding the concept of superposition of the charges, then the charge and the string problems. Then after that we'll solve some numericals regarding the equilibrium of the charges. Then after solving all these problems vividly, we'll proceed further to our next concept, that is the concept of electric field and potential. So without wasting much time, let us directly proceed to the concept of principle of superposition of the charges. So consider these two geometrical arrangements. In the first case, we have an equilateral triangle. Each side of length L, and we have three equal charges of magnitude plus Q located at the three vertices of this equilateral triangle, and we have to find out the net force on any one charged particle located at any one corner due to the other two charges. So in the second case, we have the same equilateral triangle, each side of length L, but here the arrangement of charges is something different. So this is plus Q, this is minus Q, and this is again plus Q. And we have to calculate the net force on this plus Q due to the rest two charges. So coming to the solution of the first question, so let the triangle, name of the triangle be ABC. So let us find out the net force on this plus Q due to the rest two plus Q charges located at A and B. So we have to find out the net force on this plus Q located at C. So see, this plus Q will experience two forces due to the other two charges located at A and B. So see, this is positive and this charge is also positive, so the force, it will experience a repulsive force due to this charge, and the force will be along this. So this will be the force on the charged particle located at C due to the charged particle located at A. So this is FCA, and similarly the plus Q will experience another force due to this plus Q located at B. So this will be the force on the charged particle C located at C due to the charged particle located at B. So this is FCB. Now these two forces, they are inclined at an angle of 60 degree, because by geometry this is an equilateral triangle, so each angle will be 60 degree and this angle will be also equal to 60 degree. So now there are two forces, FCB and FCA, are acting on the charged particle plus Q. Now as per the principle of superposition, the net force on this plus Q charge can be calculated by calculating the resultant of these two forces. So here FCB and FCA are the two forces acting on the charge plus Q, and they are inclined at an angle of 60 degree. So as we know that if two vectors P and Q, suppose this is vector P and this is vector Q, if they are inclined at an angle of theta, then the resultant of both of them is given by R is equal to P square plus Q square plus 2PQ cos theta square root. So this is the formula for magnitude of the resultant. So here we are having two forces, FCB and FCA, and both are inclined at an angle of 60 degree. So in order to find out the net force on this plus Q, we have to find out the sum of these two forces. That means we have to find out the resultant of these two forces. But you see, the FCB and the FCA, in both these two forces, the charges are plus Q and plus Q, and the distance in both the cases is same, L. So FCB will be equal to, the magnitude of FCB will be equal to magnitude of FCA. So that will be equal to 1 by 4 pi epsilon naught capital QQ by L square. Now let this force is equal to F for assumptions. As both the forces are equal, let us assume that FCB is equal to FCA is equal to FCA. So Now the resultant of these two can be calculated by, so the F net force on the charged particle plus Q will be equal to the resultant of these two, so it will be F square. In place of P and Q we will put F square plus 2F into F into cos, the angle between these two forces is 60 degrees, so it is cos 60 degree. So that will give us 2F square plus 2F square, and the value of cos 60 is 1 by 2. So it will be equal to 2F square plus F square square root. So that will be equal to 3F square square root is equal to root 3F. So that means the magnitude of the net force acting on this plus Q will be equal to root 3F, as we found out. Now the direction of this force, that means in which direction this root 3F will go, that can be calculated by calculating the angle made by the resultant. So as we know, the direction in which the resultant will go, that can be calculated by finding out the angle beta, and that is given by beta is equal to tan inverse Q sin theta divided by P plus Q cos theta. So that will be equal to tan inverse, in place of P and Q we will put F, so it will be F sin 60 degree because the angle is 60 divided by F plus F cos 60 degree. So that will be equal to tan inverse F sin 60 is root 3 by 2 divided by F plus F cos 60 is 1 by 2. So that will be equal to tan inverse F root 3 by 2 into, so this will be 2F plus F 3F by 2, that is 2 by 3F. So 2 will be cancelled, F will be cancelled, and that will give us tan inverse 1 by root 3, which is equal to our 30 degree. So we found out that the resultant of these two forces, the magnitude will be root 3F and the direction will be 30 degree with any of the vectors. So the net force, the magnitude of the net force acting on this plus Q will be root 3F, and it will go making an angle 30 degree with each of the vectors. So that means it will exactly go in the midline or in the midway between FCA and FCB. So it will be root 3F along the midline of FCB and FCA. So we found out that the force, the net force on this plus Q will be root 3F. That means it will be root 3 times F, means the F, that is 1 by 4 pi epsilon naught, force between the charges, so it is 1 by 4 pi epsilon naught QQ by L square. So this is the net force, F net. This is the magnitude of the force, and the direction will be along the midline or 30 degree, and it will go making an angle 30 degree with each of the two vectors, two forces. So this was the solution of the first question. Now proceeding to the next question, that is the question number 2. In the question number 2, the condition is somewhat like the question number 1, but only the sign of the charges is different, and we have to find out the net force on this plus Q due to the rest two charges. So again, let the triangle be ABC. So we have to find out the net force on the charged particle plus Q located at the corner C due to the rest two charges located at A and B. So the charged particle plus Q at C will experience two forces due to this plus Q and due to this minus Q. So this is positive and this charge is also positive, so it will be repulsive force. So the force will be along SC. So let this be force on the charged particle located at C due to the charged particle located at A. So this is FCA. And similarly, the plus q will experience another force due to the minus q, but here it is positive and this is negative, so the force will be attractive, so the direction will be along this. So this is the force on the charged particle located at C due to the charged particle located at the point B. So this is FCB. So now from the geometry, as we know, this will be 60 degree, this is 60 degree and this is 60 degree. This is an equilateral triangle. So this angle, by geometry, this angle will be equal to 120 degree. So here we got two forces, that means the plus q is experiencing two forces, that is FCB and FCA. But you can see that these two forces will be again of same magnitude, because the amount of charges in both the cases is Q1Q, and the distance in both the cases is L and L. So here the FCB will be equal to FCA, the magnitude of FCB will be equal to the magnitude of FCA will be equal to 1 by 4 pi epsilon naught capital Q by L square. So let it be is equal to Fc. So for assumption, let these two forces FCB is equal to FCA is equal to F. So now the net force on this plus Q will be again can be calculated by applying the principle of superposition. That means the net force on this plus Q will be the vector sum of the forces FCB and FCA. So now again we have to find out the resultant of these two. So the F net will be now equal to, it will be again F square plus F square, that means P square plus Q square, plus 2PQ, that means 2F into F into cos theta. So cos, here theta is 120 degree. The angle between these two forces is 120 degree, square root. So it will give us 2F square plus 2F square. The value of cos 120 is minus 1 by 2, square root. So it will be 2F square minus F square, square root. That will give us square root of F square, that is F. So we found out that in this case the net resultant, the magnitude of the resultant of these two forces will be equal to F. That means in this case we got that there are two vectors F and F inclined at an angle of 120 degree, then their resultant is also equal to F. But in which direction this F will go, that can be calculated by the direction of the resultant, that can be calculated by finding the angle made by the resultant. So here the beta will be equal to tan inverse, again it will be F Q sin theta, that means F sin 120 degree divided by P plus Q cos theta, that means F plus F cos 120 degree. So that will be equal to tan inverse F sin 120 degree is again root 3 by 2 divided by F plus F cos 120 degree is minus 1 by 2. So that will be equal to tan inverse F root 3 by 2 into, so it will be 2F minus F, that is F by 2, that is 2 by F. So F will be cancelled, 2 will be cancelled, so it will be tan inverse root 3, that will be equal to 60 degree. So here we found out that the magnitude of the net force acting on this plus Q will be equal to F, that means will be equal to both these two forces, and it will go making an angle 60 degree with the vectors. So that means here it will go in the midway of the two forces FCA and FCB. So it will be 60 degree, and the magnitude will be equal to F. Now this concept we already know from the concept of vector addition, that whenever two equal forces, that means two forces of equal magnitude, when they are inclined at an angle of 60 degree, then their resultant will be root 3f, like the previous case. So if the forces F1 is equal to F2, and if theta, in case of when it is 60 degree, the resultant magnitude of the resultant will be equal to root 3f, and the direction of the resultant will be along 30 degree. And in this case we found out that if the forces theta is equal to 120 degree, then the magnitude of the resultant will be equal to f, that means equal to both the forces, and it will go making an angle 60 degree, that means along the midline. And if the magnitude, that means if the theta is equal to 90 degree, then the magnitude of the resultant will be equal to root 2f, and the theta will be, that means the beta, it will go making an angle 45 degree. So this concept we already know from the concept of vector addition. Here we are only again reproving the concept of vector addition. So here we found out that the magnitude is equal to f, that means the net force acting on this plus q will be equal to f, that means 1 by 4 pi epsilon naught. So here f net will be equal to 1 by 4 pi epsilon naught q square by l square, and it will be go along making an angle 60 degree with both these vectors. So this is the net force acting on this plus q due to the plus q and minus q charges. Now moving to the next problem. In continuation of this concept, so we have a square. We have a square and 4 charges each of magnitude plus q are located at the 4 corners of the square. Let the square name is ABCD and the each side of length is A. And we have to find out the net force on any one charge particle due to the other 3 charges. So here what we will do, let us see that we have to find out here in this case, we will find out the net force on this plus q located at C due to the other 3 corners, the charges plus q due to located at other 3 corners A, B and D. So now this plus q will experience 3 forces due to the other 3 charges. Now see, it will experience a force due to B, A and D charge. So this will be the direction of as the forces, these 2 charges are like charges, that means positive, so they will repel each other, so this force will be repulsive, so it will be along BC. So this is the force on the charged particle located at C due to the charged particle located at B. So this is FCB. Now this charged particle will also experience another force due to the charged particle located at D. So this will be repulsive because these 2 are again positive charges, so this force will be again repulsive. So let this is the force on the charged particle located at C due to the charged particle located at D. So this is FCD. And there is another force acting on the plus q due to the plus q located at A. So this will be the force acting on this charged particle plus q due to the plus q located at A. So this is the force on the charged particle located at C due to the charged particle located at A. So this is FCA. So now there are 3 forces acting on this plus q located at C, and we can find out the net force acting on this plus q by finding out the resultant of these 3 forces as per the principle of superposition. So the net force on plus q will be the vector sum of these 3. So in order to find out the vector sum, Let us say that this is the F1, this is F2, and this is F3. Now see, here the FCD will be also equal to FCB. So here there are three forces, F1, F2 and F3, and we have to find out F1 plus F2 plus F3. So in order to do so, what we can do, we can first add the forces F1 and F2, then the resultant of these two, let it be F4, can be calculated or can be added to F3 in order to find out the net, F net. So this is the way of approach. That means we'll first add these two, then after adding these two, the result will be added to F3 in order to get the net force. So let us find out. So here FCD is equal to FCB because FCD is between plus Q and plus Q. FCB is also between plus Q and plus Q, and both are separated by the distance A. So FCD will be equal to FCB, and here the angle between them, angle between FCD and FCB is 90 degree. So here theta is equal to 90 degree. So first let us find out the resultant of these two, and after finding the resultant of these two forces, we'll add the resultant of these two with the third force in order to find out the net force on this plus Q. So here it will be the resultant, that means the resultant of these two will be equal to, let it be F4, that will be equal to F1 square plus F2 square plus 2F1 F2 cos, angle between F1 and F2 is 90 degree, so it is cos 90 degree. So that will give us F1 square plus, in place of F2 we can write it as F1 square plus 2F1 square cos 90 is 0. So it will be 2F1 square root over, that is root 2 F1. That means it will be root 2 times either of the two forces. In place of we could have been replaced F1 by F2 as well. So by doing that we could have got root 2 F2 as well. So the net resultant will be, that means if two equal forces are there and they are perpendicular to each other, then the resultant will be root 2F, the magnitude will be root 2F. So here it is root 2 F1 say, and the angle will be beta, the angle made by the resultant will be beta is equal to tan inverse Q sin theta divided by P plus Q cos theta. So it will be again F1 sin 90 Q sin theta divided by F1 plus F1 cos 90 degree. So Q sin theta divided by P plus Q cos theta, that will be equal to tan inverse F1 sin 90 is 1 and cos 90 is 0. So it will be F1 by F1. So that is tan inverse 1 is equal to 45 degree. So the resultant of these two, F1 and F2, that means FCD and FCB, will be root 2 F1, and it will go making an angle 40 degree with each of the vectors, 45 degree with each of the vectors. So that means the resultant of these two will go along this line. So this is the F4. So this is the F4, which is the resultant of F1 and F2. So but already we know that the force between the charged particle located at C and the charged particle located at A will be along the same line. It is also going making an angle 45 degree. So the F4, that means the resultant of F1 and 2 and the FCA, they are along the same line, so they are parallel vectors. So their resultant will be, that means here we will find out the F net, the net force acting on this charged particle plus Q will be equal to, it will be the sum of F4 and the FCA. So that will give us the F4, as we have found out, it is root 2 F1. So it is root 2 F1 plus FCA. FCA is given by 1 by 4 pi epsilon naught capital QQ divided by, so this distance will be root 2a. By Pythagoras theorem, this distance will be root 2a. So this is the diagonal of the square, so it is root 2a. So it is root 2a square. So that will give us root 2 into F1 is the force between these two. So it will be 1 by 4 pi epsilon naught capital QQ by a square plus 1 by 4 pi epsilon naught QQ by root 2a square. So that will give us if we will take root 2 by 4 pi epsilon naught QQ by a square common, so that will be 1 plus 1 by 2 root 2. So this is the F net, that means the net force acting on this plus Q due to the rest 3 charges, and the direction of this resultant or this net force will be along the same AC. That means this will go along this line as well. That means along the line of F4 and FCA. So we are solving these problems by taking the symbolical representations only, that means Q and Q. But if some numericals will be given, that means if some numbers will be given, the magnitude of charges will be given, then also you will proceed in the same way. That means in place of Q, you will be given certain amount of charge, suppose 6 nanocoulomb or 7 microcoulomb. If the magnitude of the charges are also given, then we will proceed in the same way as we have done in the way. So now let us move to the next problem. So here we have a same square and we are given that the square is ABCD and each side of the square is having a length A. And we are given that two corners of the square is having a charge of plus Q and Q, and the rest 2 corners are having a charge of small q and small q. So the question is, if the charge Q located at B, Q at B is under equilibrium, then what will be the relationship between capital Q and small q? Now this question seems to be a bit difficult one, but if your approach will be easier, that means if your approach will be perfect, then this can be also easily done. You see, the theme of this problem is the Q at B is under equilibrium. Now under which condition a body will be under equilibrium? That means if all the forces acting on the charged particle Q will sum up to give a resultant 0, then only Q will be under equilibrium. You see, so we will find out all the forces. Our approach will be, we will find out all the forces on this charged particle plus Q, that means Q, and we will add up them to get a resultant 0. Then only we can find out a relationship between Q and Q. So Q will be only under equilibrium if all the forces acting on this Q, their sum will be 0. And by doing so, we can also find out the relationship between small q and capital Q. So this must be the approach. So let us find out all the forces acting on the charged particle Q located at B. So here the charge Q will experience 3 forces due to the charges Q, capital Q and small q. So see, let this charge is positive, this is also positive and this is also positive. So here the charge plus Q will experience a repulsive force due to this plus Q located at C. So let this be FBC, that means force on the charged particle located at B due to the charged particle located at C. Again, this will also experience another repulsive force due to this plus Q. So this will be F, force on the charged particle located at B due to the charged particle located at A. So this will be FBA. Now the third charged particle Q will also exert a force on the charged particle located at B. But you see, the resultant of these two vectors, that means these two forces, and these two forces will be equal. You can well guess that FBC will be equal to FBA, because in both the cases it is between capital Q and small q, and the distance is in both the cases is A. So in both the cases it will be 1/4 pi epsilon naught capital Q small q divided by A square. So this is the magnitude of the force, that means FBC and FBA. So both are equal in magnitude and both are perpendicular to each other. So FBC is perpendicular to FBA. So in the previous problem, as we found out that if two forces of equal magnitude and they are acting perpendicular to each other, if the angle between them is 90 degree, then their resultant will be root 3f, that means root 2f, that means root 2. So the resultant of these two, let it be f1 and this is f2. So the resultant of these two will be either equal to root 2 f1 or root 2 f2, because f1 is equal to f2, and the resultant will go making an angle beta will be equal to 45 degree. That means it will go making an angle 45 degree. So this is f1, this is f2, this is f1, and the resultant, let it be f3, it will go making an angle 45 degree with each of the vectors. Now the fourth charge, if this charge will be positive, then it will also exert a repulsive force on this charge, because this is positive and this is positive, so the force will be repulsive and it will go along this. That means it will go, if this is your Q, so then this is also Q, and if this is positive, this is given positive, and if this charge will be also positive, then the force will be repulsive and it will go along the same line as F3, in the same direction of F3. So their resultant can never be equal to 0. So if this charge will be positive, then the resultant of these two and the force between Q and Q will go in the same direction and they can never cancel each other. So the resultant of these forces, 3 forces, can never be equal to 0. So the only condition in which the Q can be under equilibrium is that if this charge will be negative. If this charge will be negative, then this is positive and this is negative, so it will attract the charge, so the direction of the force will be along this. So if this will be negative, so the direction of the force will get reversed and this will be along this. So the resultant of these two will be in this direction, and if it will be minus Q, so the direction of the force in between these two will be in this direction. so they may cancel each other if their magnitude will be equal. So this is the formula, or this is the fundamental behind this question. So here definitely this charge must be of negative nature, because only then the plus q can be under equilibrium, and we are given that the plus q is under equilibrium. That means this charge must be negative. So see, so this F3, as we have find out, the F3 will be equal to the resultant of these two, so it will be root 2 F1. That means it will be root 2 into 1 by 4 pi epsilon naught QQ by A square. And the magnitude of this force between plus q and this minus q will be equal to, let it be F4. So that will be equal to 1 by 4 pi epsilon naught QQ by, and this distance is root 2a, so it will be root 2a whole square. So that will give us 1 by 4 pi epsilon naught QQ by 2a square. Now the charge plus q will be only under equilibrium when these two forces, that means F3, so this F3 is going along this direction and this is F4, so F3 is the resultant of F1 and F2, and as we have found out, so the q will be under equilibrium only when the F3 will be equal to F4, because they are opposite in direction, and when they will have equal magnitude, then only they will cancel each other. So in order to have a resultant 0 at plus q, the F3 must be equal to F4. So here F3 is root 2 times capital 1 by 4 pi epsilon naught capital Q small q divided by a square, and that must be equal to 1 by 4 pi epsilon naught QQ by 2a square. So that will be equal to, that implies, so here capital Q will be cancelled, this will be cancelled, a square will be cancelled, so we will get root 2 small q is equal to capital Q by 2. So that implies our small q is equal to q by 2 root 2. So this is the relationship between capital Q and small q if the plus q is under equilibrium. So this was the solution to the problem number 4. Now we'll move forward further to the next problem. And the next problem is, here we again have an equilateral triangle ABC, each side of length L, and again three charges each of magnitude plus q are located at the three corners of the equilateral triangle, and we have to find out the net force on a charged particle q which is located at the centroid of the triangle. So in order to solve this question, we must have some geometrical idea. That means if this is the centroid of the triangle, it must be located at equal distance from A, B and C. So the centroid must be located at equal distance from all the three corners or all the three vertices of this equilateral triangle. Now let the centroid be O. So this charge q, when it will be placed at the centroid, it will experience three forces due to the plus q, all the three plus q charges located at the corners A, B and C. So now this is positive, so this charge is positive, so this force will be repulsive. So this will be along AO. Again this is positive and this charge is positive, so this will be along CO, and this is positive, this is also positive, so this will be again along BO. So these are the forces. So this is, let this force be FOB, force on the charged particle located at O due to the charged particle located at B. Similarly this will be FOA and this will be FOC. So now we have got three forces acting on the charged particle small q. So the three forces, if we will redraw it, so this will look like this. So this is FOB, this is FOC, and this is FOA. So from geometry, each angle will be 120 degree. Now this formula or this representation can also be done in another way, that if this is the FOB and this is FOC, which can be drawn at the head of the first. So this is FOC and FOA. So this is FOA, and you can see these three vectors, this is FOA. So these three vectors, they are represented by the three sides of a triangle, all taken in same order. That means they are forming a closed triangle, because each angle is 120 degree, so it will definitely form a closed triangle. And in this case, and this, all the three forces are equal in magnitude also. See, because as the centroid is located at equal distance from all the corners, so this distance and this distance and this distance will be equal. So let it be A. So these three distances of the centroid from all the three corners will be equal. So definitely the FOC will be equal to FOB will be equal to FOA, because in all the cases the force is between the charge plus q and small q, and in all the cases the distance is A. So these three forces will be equal in magnitude, and they can be represented by the sides of a closed triangle, that means all taken in same order. So definitely their resultant must be equal to 0. In another way, we can also see that if these are two vectors FOC and FOB were inclined at an, so this FOC equal to FOB, and the angle between them is 120 degrees, so it will exactly go along the midline joining the two forces. So this will go making an angle 60 degree, and this will be also, the resultant will be also equal to F, that means equal to these two. So, and this is also equal to both of these forces, so this will be also equal to this. Now the angle between this F and FOA is 180 degree. So this is exactly opposite to this. So these two forces, they are equal in magnitude and opposite in direction, so the net resultant will be 0. So when three equal charges are located at the three vertices of an equilateral triangle, then if another charge is placed at the centroid of the triangle, then the net force on that charge will be always is equal to 0. And the same condition will be also in other geometrical configurations, like if this is a square and it has 4 equal charges of magnitude plus q located at the 4 corners, then the net force on a charged particle small q placed at the center of the square will be also equal to 0. So here also F net will be equal to F net on small q is equal to 0, because here it is positive, so it will be repulsive. Each distance will be a by root 2, so this is also a by root 2, and the force will be repulsive in both the ways. It will be also repulsive. So from the symmetry, as this is a symmetrical body and all are equal, so from the symmetry we can say that the Q will be under equilibrium and all the forces will cancel each other. So the net force on this small q will be always equal to 0. Similarly, in case of a pentagon also, at the center of the pentagon if another charge, so 5 equal charges, they are placed at the 5 corners of this pentagon, and if another charge q, so from the symmetry you can say that now the distance of the center from each of the corner will be equal. So these 5 distances will be equal and these forces will be also equal. So from the symmetry we can say here also the F net on this plus q in the small q will be also equal to 0. Similarly, in case of a hexagon also, the net force located on a charged particle small q, if each corner is having a plus q charge, then the net force, so from the symmetry this distance, all these distances will be equal, so the net force on this charged particle located at the center O will be also F net, here it will be also equal to 0. So these questions are quite frequently asked in various competitive exams, so remember it. If you'll do a lot of practice and you draw a thorough picture in your mind that in which geometrical configuration how the forces will interact and how the net force is to be calculated. So from this concept, a frequently asked question is there. So let us solve that question as well. You see, if you are given a pentagon and 4 charges, each of magnitude plus q, are located at the 4 corners of this pentagon. So if this is the center, so all the distances must be equal, so let it be A. So we are asked to calculate the net force on a charged particle small q located at the center of this pentagon. Now this problem can be done in 2 ways. You see, because in case of a pentagon each angle will be 72 degree. But if we calculate, if we find all the forces acting on the charged particle q, and then you will find out the resultant of all these forces to find out the net force on q, the process will be too clumsy here. So there are 2 easy ways in which this problem can be easily dealt. You see, you imagine another plus q at the fifth corner of this pentagon. If another plus q would have been there, then the net resultant force on this plus q would have been 0. So that means if another plus q would have been placed here, then the F net on this plus q should be equal to 0. That means let these forces be F1, that means the force between small q and this q is F1, this is F2, this is F3, and this is F4, and this is F5. So as per the geometry, from the symmetry, we can say that the F1 plus F2 plus F3 plus F4 plus F5 must have been 0. But here we don't have the F5, we only have this force. That means we have to find out the net force on this charge small q due to the charges, due to the 4 charges. That means q, q, q and q. That means we have to find out the net resultant of F1, F2, F3 and F4. But F5 is not there. But we have only assumed that if plus q would have been placed at the fifth corner, let these corners be A, B, C, D and E. So if plus q would have been at the corner E, then the resultant must have been 0. So the resultant of these 4, that means F1 plus F2 plus F3 plus F4 must be equal to the negative of F5. So that will give us, that means we can only simply calculate the F5. So the F5 will be equal to, so it is small q and capital Q separated by distance A. So the F5 will be equal to 1 by 4 pi epsilon naught capital Q small q divided by A square, and it must be negative. So that means, so the resultant of F1 plus F2 plus F3 plus F4 will be equal to minus 1 by 4 pi epsilon naught q by A square. So this is the easiest way of solving this problem, because if we will take the magnitude of each force, then we will calculate the resultant of these 4, then the process will be too clumsier. Now another way of solving this problem is that you simultaneously place a plus q and minus q charge at the corner E. So the forces due to all these 5 charges, by virtue of symmetry, their resultant will be 0 due to this plus q. And if you will place plus q and minus q simultaneously, then the net charge at E is again 0. So you can place the plus q and minus q side by side. So this plus q, due to presence of this plus q, the net force on the center charge will be 0. So leaving behind the minus q charge. So there will be only a minus q charge and a q charge, and the force between them will be, F will be equal to 1 by 4 pi epsilon naught minus q into q divided by A square. So it will be minus 1 by 4 pi epsilon naught q by A square. So by this way you can also find out the solution of this problem. Let's now discuss regarding the concept of charges and the strings in details. You see, if there are 2 charges, q1 and q2, is hanging from a rigid support from the same point by means of 2 non-conducting strings, then as the 2 charges are like charges, so they will repel each other and they will tend to push each other, so that the charges will move away from each other and at a certain distance they will be fixed. So the strings will make an angle between them, or the strings will make certain angle with the vertical. So let the masses of these two charges be m1 and m2. So let us assume that the charge q1 is making an angle θ1 with the vertical, and the charge q2 is making an angle θ2 with the vertical under equilibrium. That means when the charges will be pushed maximum distance away from each other, and at certain points they will be fixed. So under that condition, let the mass or charge q1 is making an angle θ1 with the vertical, and the charge q2 is making an angle θ2 with the vertical. So if you analyze the forces here, then let us draw all the forces. So as this is having a mass m1, so its weight will be m1g acting vertically downwards. Similarly, this mass m2, it will have a weight of m2g acting vertically downwards. Now as these are two charges also, so there will be an electrostatic force between these two charges. So as these are like charges, so the electrostatic force will be repulsive. So this is the electrostatic force, and this will be also equal here in this case. So this is also Fe. So as the electrostatic force is a central force, so it will act along the line joining the two charges. Now as the weight is acting downwards, and as the charges are pushing themselves with the electrostatic force, then there will be a tension developed in the string which will act in the upward direction. So as there are two strings and the masses are also different, so let the tension developed in this string is T1 and the tension developed in this string is T2. Now you see, this angle will be also equal to θ1 by geometry, and this angle will be also equal to θ2 by geometry. So now this will be, if you resolve this vector T1 or the tension T1, so this will be T cos theta, because if you are resolving resolution of vector, that means if you are resoluting this vector, that means the component of T1 along this direction, vertical direction, because this component will be along theta, so it will be T1 cos theta. So always remember, towards theta the component will be cos theta, and against theta the component will be sin theta. So these are the two rectangular components of T1. So it will be T1 cos theta in vertically upward direction, and this will be T1 sin theta. So sorry, this will be T1 cos theta 1, and this will be T1 sin theta 1. Similarly, this component will be T2 cos theta 2, and this component will be T2 sin theta 2. So under equilibrium, as we know from the concept of equilibrium, that under equilibrium all the forces acting on the body, they must balance each other. That means the net resultant of all the forces acting on the body must be 0. That means in this case the forces acting in vertical upward direction must be balanced by the forces in downward direction, and the forces acting towards the right must be balanced by the forces acting towards the left. So the net upward force must be equal to net downward force. So in this case it will be, so the T1 cos theta 1 will balance the weight m1g, and the T1 sin theta 1 will balance the electrostatic force Fe. So if this is equation 1 and this is equation 2, so dividing equation 1 by 2 will get that the tan theta 1 will be equal to Fe by m1g. And similarly also from this mass m2 we can get tan theta 2 will be equal to Fe by m2g. Now from these two formula we can compare the forces. That means you see, if m1 will be equal to m2, that means if the mass of both the charges will be equal, under that condition theta 1 will be equal to theta 2. So that means the angle made by the charges with the vertical will depend upon the mass of the charges. It is quite obvious from this formula. So the angle, this angle made with the vertical by the strings will depend upon the masses of the charges. So if both the charges are having equal mass, then the angle made by the masses with the vertical will also be equal. So if m1 is equal to m2, then theta 1 will be equal to theta 2. So so both the strings will make equal angle with the vertical. Now if m1 will be greater than m2, then theta 1 will be less than theta 2. So it is quite obvious, because both are experiencing equal amount of forces, repulsive forces, but if this mass will be greater, then it will be pulled more by the earth. That means the weight will be more, so it cannot go up to a greater extent, up to a greater distance, so the angle will be definitely smaller. So if the mass will increase, the angle will also decrease. So here, if m1 is greater than m2, then theta 1 will be less than theta 2, and reversely we can say, if m2 is greater than m1, then theta 2 will be less than theta 1. So definitely the charge which is having higher mass will make a lesser angle with the vertical, and the charge which is having a less mass will make greater angle with the vertical. So this is the fundamental, and this is the approach to this charge and string problem. Now in another case, so this was a generalized concept. Now let us go to another concept of this charge and string. See, suppose there are two equal charges, that means equal in all respect, that means having same charge and same mass as well. So if there are two equal charges, each of magnitude q, and each having a mass m, they are hanging from a rigid support from the same point by means of two non-conducting strings, then let us analyze all the forces on this. So let the length of the strings be L. In both the strings, the length is L. Then let us analyze all the forces acting on these charges. So you will see, if this is mass m, so there will be weight mg acting vertically downwards. In this case also the weight will be mg acting vertically downwards. Now as these are like charges, so the force will be repulsive. So let this is the electrostatic force. So this will be also same as the previous one, and by virtue of these forces a tension will be developed in the string. Now from the previous problem we know that if the two masses will be equal, so these two charges or the strings will incline at equal angles with the vertical. So this will be theta, and this angle will be also equal to theta. So now as the charges, they will move away from each other. So under equilibrium, when equilibrium will be reached, that means when the charges will remain maximum distance away from each other, let the distance be x. That means when the charges are equilibrium, they are separated by a distance x. Now again, as this angle is theta, so this angle will be also equal to theta. So this will be t cos theta, and this component in the horizontal direction it will be t sin theta. So here it is again, the angle will be theta, so this will be t cos theta, and this will be t sin theta. Always remember, towards theta, that means if theta is with this is the vertical, and this is the angle theta made with the vertical by this string, so towards theta the component will be t cos theta, and against theta the component will be t sin theta. So here also it is t cos theta along the direction of theta, and in the opposite direction of theta this is t sin theta. So under equilibrium we can say the net vertical force, that means the net upward force, will be balanced by the net downward force. So t cos theta will be equal to mg, and the net forces towards the right will be balanced by the net force towards the left. So T sin theta will be equal to Fe, electrostatic force between the charges. So now on dividing this equation 1 by 2, we'll get that the tan theta will be equal to Fe by mg. Now this is one formula, because if you are given the magnitude of the charges and the distance between them, the x, then so this formula will be applied when if the charges are given, q is given, now the x is given and the m is given. So by looking at the problem, you can easily sort out which formula is to be applied, because here tan theta will be Fe by mg. Then if you are asked, then if q, x and m is given and you are asked to find out the angle made by the charges with the vertical, then the theta will be equal to tan inverse Fe by mg. But remember, the angle made by the strings or the angle between the strings, in order to find out the angle between the strings, the angle is not theta. So it is theta plus theta is 2 theta. So always remember, the whatever angle you will find out by applying this formula, theta is equal to tan inverse Fe by mg, in order to find the angle between the strings, if it is asked, then the angle will be 2 theta. Remember it. So now reversely, you can see that suppose this Fe and mg are not given, you are only given that the length of the string is L, that means the length of the string from which the charges are hanging, both are having a length L, and under equilibrium let the charges are separated by a distance x. Then you can see, if you will put, suppose this is O, this is A and this is B, and let this is the center of this line, let it be D. So you can see in the triangle OAD, this OAD triangle, if you will take the sin theta, then the sin theta will be equal to, so sin theta is P by H, so it will be this length AD. So AD will be nothing but x by 2, because the entire length is x, so this is the midpoint, D is the midpoint, so the AD will be equal to x by 2. So sin theta will be equal to P by H, so it will be x by 2 by the H is L. So it will be x by 2 divided by L, so that will be equal to x by 2L. Or you can say the theta will be equal to sin inverse x by 2L. So now this is also another formula to find out the angle between the strings, or the angle made by the string with the vertical. And so if the x is given and the length of the string is given, so you can apply this formula in order to find out the angle between the strings. Now so from this we can also get the x will be equal to 2L sin theta. So reversely, if the angle between the strings is given, remember the theta will be, you have to divide it by 2. If the angle between the strings is given, then here theta is not the angle between the strings, it is the angle made by the string with the vertical. Then if the total angle is given, entire angle is theta is given in numericals, then you have to divide it by 2. You put theta by 2 here. That means if the angle made between the strings is given, that is 60 degree, then here the theta will be 30 degree. So because this is the half angle, not the entire angle, so this will be whatever angle is given, you put the half of that angle. So x will be 12 sin theta. Now the if length of the string is given and the angle made between the strings is given, and you are asked to find out at what distance the charges will go, what maximum distance the charges will go, that will be the x, and this can be calculated by the formula 12 sin theta. So from this conclusion, from this formula, one question is very frequently asked, that is, if this is the condition, that means if two equal charges having charges q and mass and equal mass, if they are hanging from a rigid support by means of two strings of length L, then prove that the q square will be equal to 4 mg L square sin square theta tan theta 4 pi epsilon naught. Now this is a very frequently asked question, and this is quite a bit easy one. You see, as we got that the tan theta is equal to Fe by mg, so that implies the tan theta will be equal to, in place of Fe we can put, so the Fe is between q and q separated by the distance x, so it will be 1 by 4 pi epsilon naught q square by square of the distance, that means it will be here, it will be x square divided by mg. So that implies we can write the q square will be equal to, so it will be mg tan theta 4 pi epsilon naught x square. Now from the geometry of this figure we can see that if we will take the sine of this angle again, here the sine theta will be equal to x by 2 divided by L, because it will be p by h, so this is x by 2 and this is x by 2, so this will be x by 2 divided by L. Sine theta will be x by 2 p by h, so it will be x by 2 divided by L. So that implies so here it will be sine theta is equal to x by 2L, or the x will be equal to 2L sine theta. So in place of this x we can directly put 2L by sine theta, 2L sine theta, so it will give us the q square will be equal to mg tan theta 4 pi epsilon naught. In place of x we will put the value 2L sine theta, so q square will be equal to mg tan theta 4 pi epsilon naught. In place of x it is 2L sine theta whole square, so it will be 4 mg L square sin square theta tan theta 4 pi epsilon naught. So this is the q square, and hence proved. This is the question which is asked, and this is quite a bit easy one. Now in some problems the values of q and q will be given, so from this formula, these two formula, that is the tan theta, quite relevant one, tan theta is equal to Fe by mg, you can directly remember this, and the sin theta is equal to the x by 2L. Now from these two formulas we can easily find out the unknown quantities. That means if theta is asked or if charges will be asked, that means q can be also asked. So don't forget that this Fe will be equal to 1 by 4 pi epsilon naught q square by x square. So from that you can also find out the q. So whatever quantity will be asked, you can find them by these formulas. Now moving to the next problem, which is a bit difficult one and very frequently asked in various medical entrances, that suppose this exact system of chairs is dipped in water. This is the same condition, that means two charges each of magnitude q having masses, equal masses, they are hanging from a rigid support from the same point by means of two non-conducting strings. Now we have already drawn all the forces acting on the charges here. Now if this entire system is dipped in another liquid of dielectric constant K, suppose, so let us see that this entire system is immersed in another liquid of dielectric constant K. So that dielectric constant of that liquid is K, and the density of the liquid is given sigma, and given that the density of this body is rho. Each body is having a density rho. So when this entire system is dipped in dipped in a liquid of dielectric constant K, then we are asked to find out such that when this system is dipped in that liquid, the angle made by the vertical does not change, or the angle between the strings, it does not change, it remains the same. So in that case, you are asked to find out the dielectric constant K. So the question is something like that two equal charges of having equal mass, they are hanging from a rigid support from the same point by means of two non-conducting non-conducting strings. Now when this entire system is dipped in a liquid of dielectric constant K and having density sigma, such that the angle between the strings does not change. That means when it was placed in air, suppose the angle was this, the entire angle was theta, total angle was theta, and when this is brought in or dipped in the medium of that liquid medium, then the angle also does not change. That means here also this is theta and this is theta. So after dipping this entire system in that liquid, the angle does not change. So in that condition, you are asked to find out the dielectric constant of the liquid. So hence, find out the dielectric constant of the liquid under which condition and under what value of K, so this angle will not change. Or reversely, if this angle is not changing after dipping this entire system in the liquid, you have to find out the dielectric constant of that liquid. So here you can see that when this entire system will be dipped in that liquid of dielectric constant K, now this is having a charge Q again, and the masses are equal. But let us redraw the forces acting on this charge inside the liquid. So see, now here the weight will be acting downward, but it will not be equal to mg. So as we know, when a body will be immersed in liquid or it will dipped in a liquid, then an upthrust will act upward in upward direction by the liquid. So the liquid will put a upthrust in the body, on the body in the upward direction. So this weight will not be mg, so the weight of the charge q will now decrease. So that will be equal to, as we know, the upthrust will be v, the density of the liquid. So it will be v, density of the liquid is sigma, p sigma g. So the net mass weight of the body will now become mg minus v sigma g. So this will be the net weight of the charge inside the liquid medium, and here the force between the charges will be, now electrostatic force will be equal to Fe. It was in the air, it was Fe, but here the force will definitely decrease, because as we know, whenever the charges and dielectric medium is introduced between the charges having dielectric constant K, then the force between them is reduced by the dielectric constant, by the factor dielectric constant. That means here the new force in that medium, that means the F medium, the force in the, here this will not be equal to Fe, so it will be Fm, that means force in the medium. So that force in the medium, liquid medium, that will be equal to Fe by K, as we know from our previous chapters, that the force in that medium will be force in the air divided by the dielectric constant of the medium. So here, that means here the force inside the liquid, it will be decreased by the factor K. So here the force will be, or in place of it will, you can write also it will be Fe by K. So here it will also be Fe by K. And as the mass is different in the liquid, and this electrostatic force is also different, so the tension will be also changed. So this tension, let it be T1. So here, but the angle remains the same. So here this will be also theta. So it will be T1 cos theta and this will be T1 sin theta. So if we'll compare these two, that means when the charges are in air with the condition when the charges are dipped inside the liquid, we will find that when the charges are in air, so we got that the tan theta will be equal to Fe by mg. But when inside the liquid, you will see that this T1 cos theta, again this is T1 cos theta is equal to mg minus V sigma g, and the T1 sin theta will be equal to Fe by k. So that implies, again it will be dividing this equation 1 by equation this 2, you will get that the tan theta will be equal to Fe divided by k mg minus V rho g, sorry, V sigma g. Now from these two we can write that, from these two, comparing these two equations, we can write that the mg will be equal, as tan theta is equal, Fe is equal to equal, so we can write that the mg will be equal to k times mg minus V sigma g. So the k will be equal to, given by, k is given by mg divided by mg minus V sigma g. But as we know that the mass of the body can be written, we know that the density, here is given that the density of the liquid is sigma and the density of the body is given by rho. So the mass of the body is given, as we know density is equal to, so the rho for the solid body will be equal to, so density is equal to mass by volume, let V is the volume of the body. So here rho will be mass by volume, so we can, in place of mass we can write it as volume into density. So here it will be V rho g, that is the volume, this is the weight of the solid, and divided by, this is again weight of the solid, so mg, so it will be again V rho g minus, this is the upthrust by the liquid, so it is V volume of that body, this is the sigma, this is the density of the liquid, into g. So remember, all the volumes are the volumes of the body, but here this rho is the density of the solid body, whereas this sigma is the density of the liquid. So from this we can directly write as so that will be equal to, so V rho Vg will be cancelled, so it will be rho by rho minus sigma, so that is equal to k. So this is the direct formula by which you can calculate the dielectric constant of the liquid. So in your competitive entrances, you only remember this formula, that means the dielectric constant k will be equal to, this is the density of the solid divided by density of the solid minus density of the liquid. So this is the direct formula by which we can calculate the dielectric constant of that medium. So these were some conceptual questions regarding the charges and the strings, and I hope that all the concepts have been well clear, and if you have any doubt further, you can also comment in our comment box.